chapter 7, I believe. So last time we talked about equations and how to properly balance equations. So remember that when we do balance equations, it is only the coefficient that we should change and only the coefficient we should change. The goal here is, as we did, to end up with really the same number of elements on each side of the arrow. And that is really based on the conservation of mass. As we've talked about, chemical reactions only involve the breaking of bonds, which are electrons. So since we really don't play with anything in the nucleus, which is our protons, which is really what determines sort of what elements we deal with, we do have conservation of elements. So if you started with 3 carbons, you should end with 3 carbons. They will be in different things on the other side. So the goal here is to end up with the same amount on each side by doing these coefficients. When you are done balancing your equation, basically 2 things has to be. You basically need all whole numbers for your coefficients, and they should be the simplest set of whole numbers. So as we talked about last time, again, if you maybe balance an equation where, you use, say, these numbers here, although it may be balanced at this point, you could definitely go through and simplify everybody by dividing by 2, really, by everybody. And you should do that to get the properly balanced equation, which would look something like this. We also saw a couple of examples where there may be necessary to, for example, use a fraction to balance the equation. And you could definitely use a fraction to balance the equation. When you have a fraction, you'll have 2 numbers, obviously. The number on top is typically the number you need to balance the equation. And usually the number on the bottom will match the subscript that is there. For example, say if this was O2, it would match, say, that 2 that is there to balance it out. So that's how you could pick the right fraction. You do need to clear it at the end so that you do end up with all whole numbers. So you cannot leave the fraction, can't have a decimal point or anything like that. So it's got to be all whole numbers. So again, to clear a fraction at the end, you can multiply everyone by the denominator. And that will clear the fraction and give you all whole numbers, and it should still be balanced if you do that correctly. The other thing that we talked about as well at the end is sometimes you will have perhaps equations that have like polyatomic ions in it. And when you do have these polyatomic ions, a lot of times it's easier to balance these equations by keeping the polyatomic ions together and just kind of balance them as whole units. And as we saw there, it kind of will go relatively quickly. And as you balance those whole units, whatever it's attached to is where you go next, and you kind of go back and forth, and everything should fall into place. You should always, in chemistry, no matter what the situation is, double check that your equation is balanced. If you see coefficients, it's probably balanced, but just in case, you should double check it. There's pretty much no situation in chemistry where you should use an unbalanced equation. So you want to make sure that it's definitely always balanced when you go to use it. So just double check that it is balanced before you perhaps go on and do any type of calculations, because it should always be balanced. Any questions on balancing equations here? Okay. So now we're going to talk about types of reactions and ways to classify chemical reactions. And there's really kind of 2 big categories of classifications. One is a redox classification. So a redox reaction. And the other is a double displacement reaction. Pretty much all reactions fall under one of these 2 big categories. And there's really three reasons why a reaction takes place. So there's really a reason why a reaction takes place. And the three sort of reasons a reaction takes place is the making of a solid, which is sometimes referred to as a precipitate, PPT, the making of water, which is H2O, and lastly, an electron transfer happening. So these big classifications of reactions are really, you can think of them as sort of the big umbrella for which more specific classifications can happen. So as we will see, there are ways that you can classify the same reaction in several different ways, depending on sort of what you're looking at. So it is possible to look at one reaction and kind of classify it in multiple ways, really more specific ways along the way. But ultimately, they fall under really one of these two umbrellas in terms of types of reactions. And what each one of these guys do is, for example, redox is all about reactions where electrons are transferred. Well, double displacement is all about making a precipitate, making a solid or water. So again, between these two sort of big categories, they take care of all three reasons why a reaction takes place. And you can really boil it down to one of these two things happening, either a double displacement reaction or a redox reaction, which obviously we'll talk about what both of these are here in just a second. Any questions on that there? So we're going to start with redox reactions and talk sort of broadly about what those type of reactions are. And then we'll see more specific sort of classifications that fall under a redox reaction, where again, you can kind of classify the reaction slightly different as well. So redox reactions is short for oxidation reduction reactions, and these are redox reactions. And that's again what redox basically stands for. And those terms do mean something. So in general, there are multiple definitions of oxidation, but the one very commonly used is it is a situation where you lose electrons, is the thing getting oxidized. Reduction is the thing that gains electrons. So the good news is it always happens together. So if somebody gets oxidized, there should be somebody that gets reduced. So half of the battle is this. If you could just figure out one of them, then you know the other guy is doing the opposite thing, because they always do occur together. Some people remember this as Leo the lion goes grr, loss of electrons oxidation, gaining of electrons reduction. Some people like the oil rig, oxidizing is losing, reducing is gaining. You could put Leo the lion on the oil rig and he goes grr. You don't have to choose. You could use them both in that case if you like. There are some other definitions, as we will see, but these are the two main ones. So how do we know if something is perhaps going through oxidation or going through reduction? So we should think about it in terms of what is happening on sort of opposite sides of the arrows. So as a species goes from one side of the arrow to the other, is it losing electrons or gaining electrons? And we should first think about what it means when something loses electrons. So what does it mean when something loses electrons? Does that substance get more positive or more negative if it loses electrons? It should get more positive, right? Because it lost electrons, which means it has more protons, which are positive. So it should become more positive. So things that lose electrons tend to become more positive, and things that gain electrons tend to be more negative, obviously, for the same sort of reasoning. If it gains electrons, which are negative, it now has more electrons, which are negative, than positive protons. So it becomes more negative. So a very simple sort of way to figure out, you know, did this thing go through oxidation or reduction is a basic number line. And usually on a basic number line, we have 0, and to the right there are positive numbers, and to the left there are negative numbers. So if you look at the charge, which is really the oxidation state, but we will call it the charge of a substance on the left-hand side of the arrow to the right-hand side of the arrow, or the element on the left-hand side of the arrow to the right-hand side of the arrow, and you see that its oxidation state or charge becomes more positive, or simply it is moving in this direction on the number line. That thing is going through oxidation. If you see something on the left-hand side of the arrow to the right-hand side of the arrow, and the charge or oxidation state is becoming more negative or moving in this direction on the number line, that substance is going through reduction. So if we look at something, say like calcium plus some oxygen, goes a little calcium oxide, and do a little balancing because we are chemistry students here. There we go, a little balancing there. So here we have really two elements when we look at this, right? And I think we've talked about this, but just in case we haven't, let's make sure. If we have any type of element that is by itself, not combined with anything, does it have a charge? It does not. So things, again, only get charges like when they make ionic compounds, when a metal and a non-metal come together. So when we look at calcium on this side, it basically has no charge or oxidation state. The oxygen, that is naturally how oxygen comes as a diatomic molecule. It also doesn't have one. But when those two come together on the right-hand side, does that calcium have a charge? It does, right? Because that's a metal and a non-metal. That's an ionic compound. Calcium is group number 2, which means it has a +2 charge. Oxygen is group number 6, which means it has a -2 charge. Yeah. And that is when these guys gain charges, metals and non-metals, right? When they come together, you get those transfer of electrons, which is why this is a redox reaction that is taking place in this case. First off, any questions on that? So now we can very simply figure out who's being oxidized and who is being reduced by simply looking at the calcium on the left, which started at 0. And my calcium on the right ended with a +2, which means it's moving in this direction. So that means the calcium here is being oxidized or reduced. Which way is it moving? It's moving to the right. So it is being oxidized. So the calcium here is being oxidized or going through oxidation. The nice thing about this is if I could figure that out, I know by default, without figuring anything else out, it is the oxygen here that is actually getting reduced or going through reduction. And we could figure that out the same way. We see the oxygen on the right-hand or left-hand side of the arrow is starting at 0. So that would be somewhere here. And the oxygen on the right-hand side ends at -2, which means it is moving in this direction, more negative, right, on the number line, as our negative numbers are there to the left, and it is going through reduction here. So as long as you can figure out one, you can figure out the other. And this is actually a redox reaction that is taking place. There's actually the electrons that are being transferred from the calcium to the oxygen, right? So it's losing a couple of electrons. Oxygen is gaining a couple electrons. That is one of the reasons why a reaction takes place, this electron transfer that's actually happening. So this reaction here does fall under the big umbrella of a redox reaction that is taking place. We see the electrons being transferred here. Any questions on that there? So let's take a look at our sodium chloride here. So here, sodium is all by itself, has no charge. Chlorine, that again is how it naturally comes, has no charge. But when those two come together, that is an ionic compound, right? That is sodium chloride on the right-hand side. And that sodium has a +1 charge, as that's group number 1. And my chloride, which is group number 7, has a -1 charge. So once again here, if you're not sure, we have our 0, we have our plus, we have our negative numbers. We'll take a look at the sodium, which starts at 0 on the left-hand side, and on the right-hand side ends at +1, which means it is moving in the positive direction here. And that means that it is going through oxidation, the sodium. So this guy here is going through oxidation, or being oxidized. The chlorine is starting at 0 on the left, and on the right-hand side ends at -1. And that means that it's becoming more negative, and it is going through reduction here. And that means that this guy is going through reduction. Once again, this always occurs together. Whatever gets oxidized or somebody gets reduced. So again, if you could just identify half of that, the other guy is doing the opposite. This is what we expect to happen, because whenever we get a metal and a non-metal together, which one should lose electrons always? Which one? It is the metal that should lose electrons, right? Whenever a metal and a non-metal come together. So whenever you have that combination of metal and non-metal coming together, we know non-metals gain electrons, right? That's why they become negative. And we know metals become positively charged because they lose electrons. So whenever we have a metal and a non-metal coming together, it should always be the metal being oxidized, and the non-metal should always be the one reduced. Any questions on that there? So what happens if I had something like this? Say iron 2 going to iron 3. Is this guy being oxidized, or is he being reduced in this case? So let us see. We'll take a look at our number line here. It is starting at +2 on the left-hand side, which would be around here, right? And it's ending at +3, which is going in this direction, right? Becoming more positive. So this guy is actually going through oxidation. Yeah. So it works really well if you don't have a negative guy, but you want to compare two positive guys, perhaps works the same way as well. So, or two negative guys as well. So again, this number line is a very simple, quick way that you can basically figure out what is being oxidized, what is being reduced, simply by following. It really is what is referred to as the oxidation state of these guys as you go from left to right, but we could call it the charge in this sense. Any questions on any out there? All right, so this reaction is an oxidation reaction. If we look here at our magnesium and our oxygen, making some magnesium oxide, once again, that is going to be 0, as that's the element by itself, not combined with anybody else. That is also going to be 0, which is, again, not combined with anybody else, our non-metal. When these two guys get together in our ion compound, we got our +2 and our -2 for oxygen, which is group number 6. These charges are just coming from, like we did when we talked about naming and the periodic table. Once again here, if we look at magnesium, magnesium is starting at 0, ending at +2. So again, becoming more positive here. So our magnesium is being oxidized or going through oxidation. By default, that means that my O2 will be reduced. And we can also see that if we go at 0 for O2, on the right-hand side, it is -2. So it is going in that direction, becoming more negative and going through reduction in this case. Any questions on that? Yeah. How do I get -2 for the oxygen? So it's just like what we talked about when we did naming, right? The periodic table. When we have an ionic compound and ions, everybody in group 1 is +1, right? Everybody in group 2 is +2. So oxygen is over here in group 6, which is -2. Yeah. And that's how we also got the +2, obviously, for the magnesium in this case as well. And again, they only get those charges when they make an ionic compound. So that's why they have charges on the right-hand side of the arrow here, because they're together in an ionic compound. When they are by themselves, not combined with anything, they have no charge. So they have basically a 0 to start with. Other questions on that? Now, as we will see when we get into organic as well, we can look at oxidation and reduction involving hydrogen and oxygen. And we will see it a little bit more when we get into organic. Sort of general chemistry, inorganic chemistry, oftentimes looking at the charges is the easiest way to figure out oxidation and reduction. But a lot of times with organic chemistry, which we'll talk about later on in the semester, there are really no kind of ions and stuff. It's really all covalent bonding. So a lot of times looking at oxygen and hydrogen is the way to go. So as we just saw there, oxidation, one definition is the loss of electrons. Another definition is gaining oxygen as you go from reactants to products in a reaction. Another definition of oxidation is losing hydrogen as you go from reactants to products in a reaction or equation. Reduction has similar definitions. We saw that it is gaining electrons. It can be losing oxygen as you go from reactants to products. And it can be gaining H2 as you go from reactants to products. So these other two definitions of oxidation and reduction, we definitely will see again as we kind of go into organic chemistry a little bit later on in the semester. So we'll talk about it here. So for example, if we look at these two, if we look at the sulfur here, sulfur has 2 oxygens on the left, and over here, sulfur has 3 oxygens on the right. That means that sulfur has gained oxygen as it went from left to right. And that would mean in this case that this guy here is going through oxidation. Oxygen basically would go through reduction in this case. Now, if we look at the bottom here, copper has oxygen. Copper has no oxygen on this side. So it has lost oxygen as it went from left to right. And that would mean that it is going through reduction. Hydrogen has gained oxygen as it goes from left to right in this case, which means it will go through oxidation. In this particular case, because there's actually a metal involved, you can still do the gaining and losing of electrons here. So if we just look at the guy that has a metal, and we'll just look at those guys together. This is copper, what? Copper, oxygen is -2, which means in this case, copper is +2, yes. This is copper by itself on the right-hand side, right? Which means it has no charge. So if we look at the copper component here, we can see that the copper started at +2 and ended at 0, heading in that direction, which means that copper is going through reduction. So if you have anything that has like a metal or something like that, or a positive charge, you could kind of follow it the same way as we did before. And again, by knowing that this guy went through reduction, by default, the hydrogen here has to go through oxidation. Any questions on that? Yeah. It is actually not a polyatomic ion in that particular case. It's actually some of those type 3 compounds. So it's just SO2. Yeah, so I think we actually drew SO2. It's actually just this guy here. Looks like this. So there's no charge on this guy. You would need like SO4 2-, so it would have the charge if it was something like that. So this is not a polyatomic ion. Either side, actually, the SO3 as well. It's not a polyatomic ion. Other questions? Okay. So these are 3 very common definitions of oxidation and reduction, 2 of which, the oxygen and hydrogen, we'll see more in organic a little bit later on, but mostly this one, probably the losing and gaining electrons, is really what you could focus in on here. And again, if we look at hydrogen, carbon definitely lost some hydrogen here, which means that it is going through oxidation. And by default, that means that this is going through reduction in this particular case. All right. So now we have an idea of what a redox reaction is. We're going to see now more sort of specific classifications of redox reactions, which you could classify, again, these reactions in a more specific way. Once again, these are the 3 reasons why a reaction takes place. These 2, again, are our double displacement, which we'll talk about in a second. And we are kind of right now in the middle of looking at really kind of ones that fall under the redox umbrella. So although you can classify a redox reaction, obviously, as a redox reaction, a lot of times these reactions are classified a little bit more specifically of sort of what is taking place. And we're going to look at these specific classifications here. The first one is a synthesis or combination reaction. And a synthesis or combination reaction is basically you take two things and make one thing, hence the name combination. So these two things make one thing. This is a redox reaction overall, so it does fall under the redox umbrella, but a more specific classification of it is a synthesis or combination reaction. So just looking at this, that is two things make one thing. So that is a synthesis or combination. That is two things that make one thing. That is also a synthesis or combination reaction. Both of these are also redox reactions. So if we look at the water reaction here, this hydrogen is 0 and this oxygen is 0, as that is naturally how it comes. Oxygen here will be -2 and hydrogen actually will be +1 in this case. And what is happening if we look at our number line here, we look at the hydrogen, it starts at 0, ends at +1, our hydrogen, and it is being oxidized. Our oxygen starting at 0 ends at -2, which means it is being reduced. So although most people will call this probably a synthesis or combination reaction, it is also classified still as a redox reaction, because that is ultimately what is happening here, is that exchange of electrons. And we just did this one a second ago, I think. So 0, 0, +1, -1. So again, in this case, this guy is being oxidized. This guy is being reduced. So once again, although we would classify this as a synthesis or combination reaction, it still falls under the big umbrella of redox reaction, which is one of the reasons why this reaction takes place, is essentially electrons being transferred. So that is why this reaction is actually taking place. Any questions on that there? So the next sort of more specific classification of a reaction is kind of the opposite of this reaction, and that is a decomposition reaction. And in a decomposition reaction, unlike this one where you kind of put it together, in a decomposition reaction, you basically are going to break it apart. So this one kind of puts it together. Sort of the opposite of that is a decomposition reaction, where you start with one thing and you break it into two or more things along the way. And that is a decomposition. One thing, multiple things is the way you could recognize it. This, once again, is also falls under the umbrella of a redox reaction. This is water just going in the opposite way. So if you run an electrical current over water, you can break it apart. This is going to be +1, -2, 0, and 0. In this case, going in the opposite direction, when we look at this one, our hydrogen is starting at +1 and actually ending at 0 going in this direction. So in this case, it is the hydrogen that is actually being reduced. And the oxygen, which is -2, ending at 0, is, oxygen is going through oxidation. And that's because it's basically the opposite of putting it together. So to break it back apart, the electron's got to go the other way, basically. And that's what is happening in this case. That is mercury 2 oxide. That means that the mercury here has a +2 charge and a -2 for the oxygen. And mercury by itself, uncombined, has a 0, and oxygen has a 0. So once again, if we look at our what's happening, our mercury is starting at +2, ending at 0. So that is our mercury going from +2 to 0, and that is becoming more negative in this case, which means the mercury here is being reduced. Oxygen here is starting at -2 and ending at 0. And that means that is becoming more positive and is being oxidized. So as you can see here, although these would probably 9 times out of 10, maybe even more than that, 9.9 times out of 10, be classified as a decomposition reaction, what is truly happening here is still the redox reaction, and they do fall under that big umbrella of redox. Any questions on those two there? All right, some other reactions that fall under really the redox sort of umbrella, in addition to synthesis and decomposition reactions, is a single replacement reaction. And in a single replacement reaction, this is also a redox reaction. But what happens in this type of reaction is one of two things could occur. So we'll take a look at how we know this. First off, there should always be some type of ionic compound, which means that this is a positive and negative guy, right? That's an ionic compound, a cation and an anion together. If this guy over here is a metal, it will have no charge. But when metals do get charges, they should become positive or negative when they get a charge. Metals should become positively charged, right? So what's going to happen in this case is the metal will come in, and a badly drawn arrow will make a U-turn over there to that guy, and it will come in and actually replace the positive guy in the ionic compound. The result of that is a new ionic compound will happen, and you'll get this now has a positive charge, and you still have the C with a negative charge, and your B will come out with no charge. So the metal will come in and kick out the positive guy. It will actually lose some electrons as it does that, by the way. And the other guy will gain those electrons and come out by itself with no charge. You could also do this exact same reaction, again with an ionic compound, with a nonmetal. And nonmetals by themselves have no charge, but when they do gain a charge, they will become negatively charged. So when this nonmetal comes in, it's going to actually kick out the negative guy in there. So they kick out the same sort of charge, and that will form a new ionic compound, which will look something like this. And then the C will come out with no charge. So this is a redox reaction. This is a single replacement reaction. In order for this reaction to actually take place, whatever is coming in, so whatever is coming in, which would be either that guy or that guy, it needs to be more reactive than what it is replacing. So it needs to be more reactive than whatever is replacing for this reaction to take place. If it is not more reactive, then frankly, you will not see the reaction take place. It will not happen, basically. So for example, if we look at this one up here, this is how I know this is a single replacement reaction. I got something by itself, like a metal. I have an ionic compound, which is hydrochloric acid in this case. This zinc is going to come in and kick out the hydrogen. When hydrogen gets kicked out and hydrogen is just by itself, it comes out as H2. That is a gas. You see bubbles. Yeah, pop, pop, fizz, fizz. Not so much fizzing, but more bubbles, I would say, in this case. So you will produce this gas, and that is hydrogen by itself, which, as we've been talking about, means hydrogen has no charge in that case. Yeah. Over here, the zinc will now gain a +2 charge, and our chloride is a -1 charge in this case. By the way, the -1 here and +1 for that guy. So this is a single replacement, either a metal by itself, a non-metal by itself, and an ionic compound. You will get this reaction to occur. In this case, this reaction does occur, which means if this reaction occurs, is zinc more or less reactive than hydrogen in this case? This reaction does occur, which means in this example, zinc is more reactive than hydrogen. And that's how you know it actually occurred, this reaction. You know it is more reactive. You did the same reaction with copper metal. and react it with hydrochloric acid, you'll get no reaction. And that is because that would mean that copper is less reactive than hydrogen in this case. Yeah. So one way you could tell if these guys will work is actually to do the reaction. There's actually what is referred to as a activity series that you might sometimes come across. And usually at this level, there is basically hydrogen somewhere in the middle, a bunch of other elements above it, a bunch of other elements kind of below it. And in an activity series like this, anything that is higher on that list is more reactive than anybody lower on the list. So anybody higher on the list will replace anybody lower. Anybody lower on the list is less reactive than higher on the list. So anyone higher on list is more reactive than lower. So I don't really plan on giving you an activity series to use, but it would be given to you if you need it. But in case you come across it in a book or something like that, that is how you use it. Again, anything higher on the list, that reaction should take place if it's replacing somebody lower. But if somebody's lower on the list, it will not take place. So in our two examples here, you would find zinc higher on the list, and you would find copper lower on the list than hydrogen. And again, that's how you can make your decision as to whether or not it will actually take place. So once again, this is a single replacement reaction. This is also a redox reaction. If we take a peek at our reaction there with zinc, and if we just look at zinc, for example, here on the left-hand side of the equation, zinc is 0. On the right-hand side of the equation, zinc becomes +2. And that means that zinc is going through oxidation in this case, right? We look at the hydrogen on the left-hand side of the arrow. It is +1, which would be like here. And on the right-hand side of the arrow, it is 0, which means it is moving in this direction, our hydrogen, which means the hydrogen is being reduced. Yeah. What about the chlorine on the left-hand side? It has a -1 charge, yes? Right-hand side, chlorine has a -1 charge, which means it's sitting right there doing nothing, which means there's nothing happening with the chlorine here. It's what's referred to as a spectator ion. It's just hanging out to balance out charges, but there's nothing really happening to chlorine here as it goes from left to right. The major thing that's happening here is the zinc is laying off a couple of electrons to the hydrogen that has a +1 charge. It's picking up those 2 electrons and becoming H2 that has no charge. So it's really that electron transfer in this case between the zinc and the hydrogen that's happening. Again, the chlorine here is really just hanging out to balance out the charges. Nothing's really happening to the chlorine in this case. Any questions on that there? So once again, each of these are single replacement reactions and also redox reactions, as again, ultimately what is truly happening in all these reactions here is those electrons being transferred, which is one of the reasons why a reaction takes place. Any questions on that? All right, now we're going to talk about here the other classification of reactions, which is our double displacement reactions. And in a double displacement reaction, this is how you could recognize it basically, AB plus CD. This is 2 ionic compounds together. Got a positive guy, negative guy, positive guy, and negative guy. So whenever you get 2 ionic compounds together in a reaction, pretty much this always happens. The 2 positive guys basically switch partners. So they basically switch partners. And that gives you 2 new ionic compounds. And depending on what happens on this side, you may get a solid that forms, which is known as a precipitate, which again is another reason why a reaction takes place. Or you may make water, which once again is the third reason why a reaction takes place. So double displacement reactions basically take care of those 2 reasons why a reaction takes place. Either as a result of a double displacement reaction, you're going to make a solid or a precipitate, or you're going to make water. And that's basically what happens. And again, everybody else is electrons being transferred and redox basically happening. Any questions on that? So if we look at this reaction here, which looks maybe scary with lots of polyatomic ions in it, but ultimately, if we look at it, this is ionic and that's ionic. So that's positive, negative guy, positive and negative guy here. So what is essentially happening, if we just break this guy apart, that really is a potassium ion and a chromate ion, which is a polyatomic ion. This guy here is really a barium ion. Oops, I guess that's a barium ion. We'll make a U-turn here. This guy here is a nitrate ion. So these are really the basic units of what makes up those two guys on the left-hand side, and they're both ionic. So simply put, what happens is they switch partners on the other side. So we have our potassium that's going to go hook up with the nitrate. Why does the potassium not hook up with the barium? They both are positively charged, right? Things with same charge don't want to be together. So your only option is the positive and negative guy has to come together. If it stays with that guy, nothing happens, right? So it's got to go find the other negative guy. And that is what happens to make this guy right here, which is our potassium nitrate, is those two guys come together. That leaves us our other sort of combination that can occur. This positive guy is going to go find that negative guy, right? And that is going to make this guy right here. And that is basically your double displacement reaction in a nutshell. The result of that is these two guys, or one of these guys in this case, the barium chromate actually makes a solid when they come together. So those two guys will make a solid when it comes together. And that is also known as a precipitate. So we get this solid that is formed, and that is a precipitate, which is sometimes abbreviated as PPT. And that is why more specifically, I'll get your question right in a sec. That's why more specifically, this reaction is classified as a precipitation reaction because a solid is formed, but it is ultimately still a double displacement reaction that's happening. Yeah. Question. Why do we have? Mm-hmm. Why wouldn't it be CrO4? Yeah, so it goes back to what we were talking about with naming as well. Whenever you have an ionic compound that's positive and negative, always both in the formula and also the name, positive guy first, negative guy second. So that's always how they come together. Yeah. And this is really the right way, what I did down here, as to how you get the proper things on the right hand side. So I didn't really balance these guys, but you want to think about the basic ions, put them together correctly like we did with naming, get the correct formula on the right hand side, and then if you need to, go back and put the coefficients in. Very commonly people will, if they had just the blank arrow on that side, nothing on that side, and you had to like predict what needs to go on the right hand side of the arrow, very commonly people will look at it and go, oh, there's a 2 there with the K. I better put the 2 over there with the K as well. And you'll get the wrong sort of formula. So if you have to predict the formulas on this side, you should just think about the basic units first. Make sure you get down the correct formulas on the right-hand side. Then you should go back and balance it with the coefficients. You do not want to do those things together, which is a very common mistake people make, is they try to both balance the equation and write a chemical formula. So in case you happen to come across it, you want to get the right formulas first. Just like in nomenclature, and then balance with the coefficients. And that is the proper order to do that. But again, very commonly people try to do it together and they get the wrong formulas. They get an equation they'll never be able to balance because they don't have the right formulas. So always think about that in case you need to do that. And regardless of how many potassiums or whatever may be over here, the basic unit of potassium is a guy with a +1 charge. And that's what you want to think about. So in this case, we have our 2 positive guys switching partners. The result of this is one of those guys will make a solid. which calls this a precipitation reaction. It is also under the big umbrella of double displacement as well. Any questions on that one there? So as we see here, our double exchange or double displacement is happening, and that is how you can recognize it. That's just from PowerPoint. Two ionic compounds. This is different than single replacement where we have just one ionic compound. Yeah, so double displacement, we have two of them. Single replacement, we have only one, and that's why we just get one guy coming in and kicking out somebody else. In this case, we get both of these guys switching out partners in this case. Now, if we look at this reaction here, this is actually an acid and a base. This is hydrochloric acid, which is an acid. And this is potassium hydroxide, which is a base. Whenever you make or combine an acid and a base together, you pretty much get two things. You get our friend water, and you get what is referred to as a salt, which is an ionic compound. Basically a positive and negative guy together. This is also a double displacement reaction, and that is because this hydrochloric acid is a positive negative guy. Our potassium hydroxide is a positive and negative guy. And essentially what is happening is the H and the K are switching partners, basically, just like before. And when the H switches, or if we look at really what is happening here, that HCl is H plus and Cl minus, and that KOH is K plus and OH minus, which is a polyatomic ion. These are the two ions for each of those guys on the left-hand side of the arrow. And we're going to get our H plus gonna hook up with our OH minus, as those guys are different. When you get H plus and OH minus together, that is where water comes from in this case. Yeah. Water always comes from, when you have an acid and base together, water always comes from the H from the acid and the OH from the base. Yeah, so that is pretty much how you always get water. The salt part, or the ionic compound part, is really the two things left over at this point. So in this point, obviously, as we can see, we have potassium that's going to hook up with the chloride, which is negative, and that's going to make our salt, our potassium chloride, our ionic compound here. So in this particular case, it is a double displacement reaction that is happening. Our two positive guys are switching partners. The result of this is the third reason, or one of the three reasons why a reaction takes place. We just made water. Yeah. And that making of water is really why this reaction takes place, is ultimately acid base wants to make water. Yeah. So water is really covalently bonded. Yeah, like this. But in sort of acid-base chemistry, we sort of think of water as like HOH, and that's sort of how it comes together. And we could write the formula because there's really two hydrogens, right? And one oxygen, which is the chemical formula for it. So in this sort of application, sometimes people think of water as H and OH, and that's sort of what is happening, what is being sort of switched out in that case. Yeah. It is a covalently bonded guy, but we kind of think of it as coming as ions in this case. Yeah. Other questions? So this one is sometimes referred to as an acid-base reaction, or a acid-base neutralization reaction. It's an acid-base neutralization reaction because, to tell you the truth, it's really just water being formed. That's pretty much what's happening here. There's nothing else happening other than water is being formed. So you're kind of neutralizing everything in this particular case. So double displacement reaction is acid-base reactions, which will produce water. double displacement reactions are also precipitation reactions, which will form a solid. And just so that we are perfectly clear here, in a double displacement reaction, there is no electrons being transferred. Yeah, so everybody is the same on both sides. So we can see that because, for example, here, my potassium is +1, my potassium is +1. My chloride is -1, this guy is -1. There's no transfer of electrons that are happening in a double displacement reaction. That is only a redox reaction, which is a synthesis, decomposition, and single replacement reaction happening here. Any questions on that? By the way, the hydrogen over here is +1, and it is +1 over here. Oxygen is -2. -2 +1. So nothing is happening to any of those elements in terms of changing their charge or oxidation state. There is no electrons being transferred in a double displacement reaction, which encompasses both acid base and precipitation reaction. Yeah. That is pretty much what makes something an acid. What makes something an acid is the ability basically to produce H plus, and pretty much all acids will have H plus in it. A base, by the other hand, is something that can produce hydroxide in solution, and that is free H plus and free OH minus moving around. Now, different than acids, so to answer your question, pretty much your basic definition of an acid, most all of them will have an H plus in it, and that's technically what kind of makes it an acid. Bases, on the other hand, do not necessarily have to have OH minus in it, but they're able to produce it. So most strong bases, like potassium hydroxide that we see here, or sodium hydroxide, most strong bases will have that hydroxide in it, but actually weak bases actually don't actually have hydroxide in it, but they're able to produce OH minus, so that makes them a base. But I would say probably 99% of acids, or the definition of acids that you would come across, they would definitely have H plus in it. There is a and why I don't say 100% is because there is a definition of an acid that involves electrons being transferred, and in that particular case, you could have an acid that technically doesn't have an H plus in it, but probably 99% of the time is going to have definitely the H in it. Other questions? Okay. All right, so lastly here, we're going to talk about combustion reaction, which really goes back to also a redox reaction. And this is sort of the last classification that will fall under redox. And the example here of combustion is an organic combustion reaction that we're going to look at here. And an organic combustion reaction is an organic molecule like methane. And an organic molecule basically has carbons, hydrogens, sometimes oxygens as well. Not always needs oxygen, but sometimes have it. But basically, the way you can recognize a kind of organic combustion reaction is pretty simple. These are the three things you should look for. You should see O2 on the left, and it will always produce CO2 and water. So if you have any type of organic guy that you're reacting with oxygen, CO2 and water is the deal. That is what you get when you light your Bunsen burner. That's a combustion reaction. Your car, if you have a combustion engine, it does through a combustion reaction as it burns your gas through it. Now, there is a more generic definition of combustion, and we'll talk about that here. So more of just a generic definition of combustion is you basically just need O2 present. So pretty much if you see any reaction where there's O2 on the left-hand side of the arrow, it can be classified as a combustion reaction. So for example, if we look at this one here, which is Mg plus some oxygen, making our MgO, a little 2 there, a little 2 there. This guy, as we talked about previously, this one reaction right here, that is two things that make one thing. That's what type of reaction? This combination or synthesis, right? This is no charge, +2, -2. As we saw earlier, there is some electrons being transferred, which means this one could also be classified as a redox reaction because there's electrons being transferred. Heck, it's got O2 on the left, which means it could also be classified as a combustion reaction. Yeah. So you can see that one simple reaction can be classified in many different ways depending on what you're looking at. So I would say pick the best classification based on your choices. Yeah, that's what you're looking at. So you definitely can classify these reactions in multiple ways. Just like we saw with our precipitation reaction, can it be a double displacement reaction? Our acid-base reaction could also be a double displacement reaction. So there are multiple ways that you could classify the same reaction. It just kind of depends on the situation as to what's maybe the best classification that you would want to use. Any questions on classifying reactions there? So to summarize what we talked about here in terms of our classifications, we have really our redox, which is our big electron transfer type situation classification. We have our double displacement reactions, which takes care of both water and a precipitate being made. So under the redox umbrella, more specific classifications are your synthesis, combination, your decomposition, your single replacement reaction, or some people will call it displacement as well, and your combustion reaction. So big umbrella redox, electrons being transferred. More specific ways to classify redox reactions are those four classifications. Double displacement means either you made water or you made a solid, and more specific ways to classify this is a precipitation reaction or an acid-base neutralization reaction. And once again, there is no electrons being transferred in a double displacement reaction, only in a redox. Any questions on any of those classifications and how they kind of fall under each other? Okay, we're going to continue on here. So we have, we talked about equations, we talked about balancing equations. So now we're going to talk about some calculations that are going to help us in a couple of different areas, including with these equations. But we're going to talk about some calculations now, and we're going to talk about molar mass and Avogadro's number. Molar mass, as we'll talk about, and Avogadro's numbers, these are really conversion factors that we use, and they are found in a couple of different places, including the periodic table. But units of molar mass are grams per mole, are the typical units of molar mass. And Avogadro's number is a number that is a constant number, and we do use it to do some conversions, and we don't want to overuse it, as we'll talk about here. So let's take a look at each of these here. We're going to start with the mole, and the mole is really not the fuzzy little guy there, but it is the mole. And the abbreviation as well is MOL is the abbreviation there. So they had to cut something off, so they cut the E off, it looks like. So if you see that, that is the abbreviation for mole. And I say that because it is very common. People will see MOL and they will think molecules. So that is not the abbreviation for molecules. That is the abbreviation for moles. And what is a mole? Well, in life, we have a lot of words that represent a certain amount of something. If you have a pair of something, that's 2. If you got a dozen, that's 12. If you're old enough to remember perhaps a gross of pencils, that's 144, how they used to come. So in chemistry, we do have a word that represents a certain amount of something, and that is basically the mole. And the mole of anything, or 1 mole of anything, will equal 6.022 times 10 to the 23. These could be particles. These could be atoms, which is very common. These could be molecules. These could be pizzas, you know, shoes, whatever it may be. Probably the occasional pizza question, but probably atoms and molecules are the units that you will see the most in here. So a mole of anything will represent that number. As we will see, that number is what is referred to as Avogadro's number. And it is atoms or molecules depending on the situation of how you're doing the calculation as to what unit you can use. So really the number stays the same, but the unit can very much vary depending on sort of how you're applying it. The two most common ways, again, are going to be atoms and molecules is really the common ways that we will use Avogadro's number. So this is a mole of different substances like sulfur, iron, sodium chloride, potassium dichromate, and so forth. We'll come back to this picture in just a second and talk about it. But let's talk officially here about Avogadro's number. It's experimentally been determined to be 6.022045 times 10 to the 23. Everybody uses this number right there. This also is a scientific notation number, which definitely you want to make sure we are still using our exponent button when we punch this into our calculators so that everything comes out correctly. So here's the deal with Avogadro's number. It is really our conversion factor, and you could use it just like a conversion factor. You could say 1 mole of something is 6.022 times 10 to the 23 atoms. Or you could write another conversion factor where you put Avogadro's number up on top, 6.022 to 23 atoms per mole. So just like we talked about with dimensional analysis, you could use Avogadro's number really as a conversion factor. And it is the conversion factor that allows you to go from moles to atoms or molecules, or backwards. So that is the key as to when you should use Avogadro's number. So very commonly people want to use it in every calculation because they're like, I remember this number. Let me just throw it into everything I do there. And you shouldn't do that. So you should really only use Avogadro's number if you have a number that's in molecules or atoms and you need to convert it to moles, or you're asked to end up in a number that is atoms or molecules. If you don't see anything about atoms or molecules, you probably should just leave Avogadro's number on the sideline. Yeah. And although some people use it incorrectly, but at least they use it good incorrectly. So they kind of divide by Avogadro's number early on in the calculation and then go, I'm just going to use on the back end as well and multiply by it. So it cancels each other out. But you do not need to use Avogadro's number in every conversion. So how does this work? It works like this. If I have basically 1 mole of hydrogen, how many hydrogen atoms should I have? 6.022 times 10 to the 23 atoms of hydrogen. Yeah. If I have 1 mole of copper, how many copper atoms should I have? 6.022 times 10 to the 23 atoms of copper. Obviously, you could write 2 conversion factors for each of those. Also works for things that are not just elements by itself. If I have 1 mole of water, how many molecules of water should I have? 6.022 times 10 to the 23 molecules. Here we're going to use molecules because water is a molecule, right? The other one we use atoms because it's an element. If I have 1 mole of methane, I would have 6.022 times 10 to the 23 molecules of methane. So once again, you can write these as conversion factors, like 1 mole of hydrogen, 6.022 times 10 to the 23 atoms, are 6.022 times 10 to the 23 atoms up on top, 1 mole of hydrogen. Same thing with our other guy there, 1 mole of water would get you 6.022 times 10 to the 23 molecules of water, are 6.022 times 10 to the 23 molecules of water will give you 1 mole of water. So these are the conversion factors that you could get from any of those conversions, and we would just use them like conversion factors. We'd obviously go opposites just like we did with dimensional analysis. So if I had 2 atoms of hydrogen, right? And I want to know how many moles that would be. I should use the conversion factor where atoms is in the opposite place, just like we did when we were doing conversions, and would be that guy. And I would put 6.022 times 10 to the 23 atoms over 1 mole of hydrogen. And in my made up example here, if I find my calculator, I'm going to take 2 divided by 6.022, my exponent button, and 23 as it's positive. And that will tell me I got something like 3.321 times 10 to the minus 24 moles of hydrogen. So we use this exactly like we use conversion factors, really to go from one unit to the next. You could set it up the exact same way as we did dimensional analysis. Again, opposites cancel, right? So we want those units in opposite locations to cancel. And again, we're dividing here in this particular case. Any questions on that there? So Avogadro's number, again, just like a dozen oranges, you would have 12. Anything you have from the periodic table would be 6.022. And that is the setup. So again, if you have atoms or molecules, you would put Avogadro's number on the bottom like we just did there, basically, and divide by it. Atoms will cancel, will leave you moles. If you have moles that you're starting with and you want atoms or molecules, you will multiply by Avogadro's number and put it up on top. Moles would be opposite and they would cancel, and you would end up with atoms or, again, molecules if we were dealing with molecules in this case. So you want to set it up the exact same way. Think of it like a conversion factor because it really is a conversion factor, and just go opposite in terms of their units. Any questions on that there? Now, this conversion factor, as I mentioned, as you can see here, is what we use to go from atoms to moles, or moles back to atoms, or molecules involved in there. Another really important sort of conversion factor, which it really is the molar mass. And the molar mass is a conversion factor that we use to do 2 really important sort of calculations in chemistry. And that is basically going from grams to moles, or moles back to grams, which is something that we do a lot in chemistry. And the molar mass is actually used for that. Because we're only going from grams to moles, or moles to grams, there is no atoms or molecules, so we do not interject Avogadro's number unless there happens to be something involving atoms or molecules into that calculation. So let's take a look at molar mass. Molar mass has units of grams per mole. And when we write the molar mass of a substance, there's a couple of things. First off, the number always stays with the grams part, and it's always 1 mole. Yeah, so it's always 1 mole, and the number stays with the grams part. The molar mass is the mass of a substance in grams per mole, and it is based off of that carbon-12 isotope, which was the isotope that was used to figure out the atomic mass. So where do we find the molar mass? We find the molar mass on the periodic table. So for example, our friend hydrogen there says 1.008 is the number on the bottom. So you might remember that this number on the bottom was the atomic mass, which is in this case 1.008 AMU per atom. It is numerically equal to the molar mass in grams per mole. So it will also be, and most often used as, 1.008 grams per mole is the molar mass of hydrogen. Again, the number stays with the grams part, and it is 1 mole. You could think of this as a conversion factor, and you could use it as a conversion factor, which means you could write 1.008 grams per mole of hydrogen, or if you needed it the other way around, a mole of hydrogen is 1.008 grams. So you can use it just like a conversion factor, dimensional analysis. Typically, we go about 4 significant figures off the periodic table. So depending on your periodic table, you may have more numbers, less numbers, whatever it may be. But typically when you take that number off the periodic table, 4 significant figures is basically what you want to take off. So if you look up there for sodium, you'll see 2299 grams per mole. Like under copper, you'll see 6355 grams per mole. This also works for anybody on the periodic table, but it works for molecules as well. H2O, if I want the molar mass of water, I pretty much just add up all the parts. So if I go to the periodic table, I will see hydrogen that says 1.008. I will see oxygen, which basically will probably say 15.9999, which is basically 16. And I could get the molar mass of each of these guys, and all you have to do is just add up the parts. So there are 2 hydrogens, each at 1.008 grams per mole. That represents basically the molar mass of the hydrogens there in water. We're going to add it to basically 1 times the molar mass of oxygen, which is 16. You don't really need to multiply it by the 1, but if you like to, you can. That gives us a molar mass for water of 18.02 grams per mole. Again, it is 18.02 grams per 1 mole. And you could use that as a conversion factor, just like the other. You could say there are 18.02 grams of water in 1 mole of water, or in 1 mole of water, there are 18.02 grams of water. So you can use it like a conversion factor, like everything else. So you can do the molar mass, which always comes from the periodic table, is the number on the bottom. That number represents how many grams there are per mole of that element. And if you have a molecule, you basically just need to add up all the parts, and that gives you how many grams there are per molecule there. Any questions on that there? Now, a couple of really important things when we talk about molar mass, and very common mistakes that people make is, that's good. So let's just say, for example, we had an equation, whatever it may be, and we'll just look at, say, water, and there was like 2 waters there. And you needed to do a calculation where you needed the molar mass of water. The molar mass of water is only based off of the formula. So you should always do the molar mass based on one of the formulas, regardless if it happens to be in an equation with a bunch of coefficients in front of it, or it says 45. If you're asked for the molar mass of a particular substance, it should just be the one formula of that substance by itself, and that's how you calculate it. So we would calculate this still as 1.008 grams per mole, plus our 16 for our oxygen. That gives us the molar mass of 18.02 grams per mole. You do not want to take the 2 in front of it. That has no effect on the molar mass, just should be based off of the formula itself. Any questions on that there? How does this tie into Avogadro's number? They do tie into each other. So if we have 1 mole of hydrogen, that would be 6.022 times 10 to the 23 atoms of hydrogen, right? And that would represent how many grams? 1.008 grams of hydrogen. So they do tie into each other. If we have 1 mole of water, that would represent 6.022 times 10 to the 23 molecules of water, which would represent 18.02 grams of water. So you could potentially need to use molar mass and Avogadro's number together. For example, if you have grams and you want to go all the way to atoms, you need to go from grams to moles, moles to atoms. And that means that you would need to use Avogadro's number. If you started with so many atoms and you want to go to grams, atoms is the key word there. It means I need to use Avogadro's number to go to moles and molar mass to go to grams. So molar mass is our conversion factor to go from grams to moles. So we would divide by the molar mass from the periodic table, and our grams would cancel, and that would give us moles. If we have moles and we want grams, we will multiply by the molar mass, which also comes from the periodic table, and the moles would cancel, and that would get us grams in this case. So again, if I had 32 moles of water and I wanted to know how many grams that would be, I would take my molar mass of water, which is 18.02 grams per mole of water, or a mole of water is 18.02 grams. So in this case, I want to get rid of moles. So I'm going to use it as a conversion factor like on the left here. And that would put our 18.02 grams up on top, a mole of water on the bottom. Opposite units will cancel. I'm going to multiply 32 times 18.02. And that would tell me I got roughly 576.64 grams. In terms of significant figures, we would actually look at this number here, which is 2. This would be considered an exact number in a calculation, and that would round us to like 580 perhaps, yeah, in terms of significant figures if we were to do it like that. And that would be 580 grams of water in this case. Questions on that? So out of the two, in terms of Avogadro's number and molar mass, you probably will use molar mass way more than Avogadro's number, yeah, in later chapters and so forth. So the molar mass, being able to go from grams to moles, moles to grams, is something we do a lot in chemistry in different places, and that's a really important conversion. Avogadro's number, again, also important as well. So going back to that picture we kind of skipped a second ago, wherever that picture may be. There you go. I could go back now, maybe. No. Feel like I angered it. Come back here. There we go. All right. Let's see here. Where's that picture here? All right. So each of these represents a 1 mole sample of each of these things, right? Why are there different amounts? If we look at the periodic table for sulfur, it says 3207 underneath it, right? Which means 1 mole of sulfur is only 32 grams. We look at iron on the periodic table there, it will say something like 5585, I hope still. We see something like sodium chloride. The molar mass of sodium chloride is 2299 for the sodium plus 3545 grams per mole for the chlorine. That can give us something like 58-ish, I think. 5844 grams per mole. So although these each represent 1 mole of these guys, right? A mole of sulfur is different in terms of grams than a mole of sodium chloride. That's different than in terms of a mole of iron, which is why they all kind of look different amounts in there, even though they all do still represent a mole of each of those things. Any questions on that? And clearly, as you can see there, we have our sugar there at the end, I think. All right, so let's see. Molar mass, molar mass. So as you can see here, anything from the periodic table, you could pull that information from. Always periodic table, molar mass. Avogadro number is just a number that you always have to use. It doesn't change. So it's just like you got to think you always have that number. But molar mass, you want to go to the periodic table, grab that number on the bottom, and that's how many grams there are per mole. So we use these as conversion factors to really do those conversions: molar mass, grams to moles, moles to grams. And again, the place where you do want to use Avogadro's numbers, anywhere where it mentions atoms or molecules, either you have a number that's in that unit or you need to find a number that's in that unit. Otherwise, again, if there's no mention of those things, atoms or molecules, just leave Avogadro's number on the side and don't use it. All right, so let's take a look at a couple of examples here. Why don't you try both of these? What is how many moles of helium are there? And 5.46 grams of helium We go to helium on the periodic table. This is what it looks like. And we'll do zinc, which is 6539, I think. All right. So take a couple minutes there, calculate them up, see what you come up with. Okay, let's take a look. So first off, we really want to sort of think about the problem here and think about, a good pathway to get us to where we want to go. So in the first one, we want to know how many moles of helium are there in 5.46 grams of helium. So the first question is, do I need Avogadro's number here? I do not need Avogadro's number, as there is no mention of atoms or molecules, right? We're not trying to find them, or we're not given a number in there. So we do want to throw Avogadro's basically out the window there. Here we are looking for moles, and we are starting with grams. So we need a way to go from grams to moles. And again, that is the molar mass. That is our pathway to go from grams to moles. We can find the molar mass by going to the periodic table in this case and looking up helium and finding the number on the bottom there. And again, that is our molar mass that's going to do that, or mm, or molar mass in this case. Now that number, you might have a lot more numbers on your periodic table than those, but again, we do go to about 4 significant figures when we pull it off the periodic table. This gives us really 2 conversion factors that we could use for the molar mass. That number basically means that there are 4.003 grams of helium in every mole of helium. And that will give us a conversion factor that looks like this: 4.003 grams per mole of helium, or a conversion factor that is moles of helium over 4.003 grams. Any questions on how we got those numbers from? And again, comes from the periodic table. So here we are starting with 5.46 grams of helium, and it just becomes really a conversion factor at this point. We want to go opposites to get rid of the units. So we do not want grams. So we do want to use the conversion factor over here on the right-hand side. That has our grams in the opposite location, which basically means we're going to divide by that number. That is going to cancel out the grams of helium in this case, and that will get us here 5.4. That's right, 5.46 divided by 4.003. Going to give us 1.36 moles of helium. Yeah. Any questions on that calculation there? Looking at the second one there, we want to know in this case how many grams of zinc there are in 0.256. Again, the MOL here is moles, not molecules. So that is, again, the abbreviation for moles of zinc. So again, do we need to use Avogadro's number on this one? We do not. Again, there's no mention of atoms or molecules finding or giving us those things. So this again is going to be a molar mass situation. As in this case, we're actually going to start with moles and end up in grams. So it's still the same conversion factor. If it wasn't given to you, which it probably will not be, you would go to the periodic table and find zinc. And again, you would see that number there on the bottom, and that it will give you your 2 conversion factors that you could use. That means that for zinc, there are 6539 grams per mole of zinc, or a mole of zinc is 65.39 grams. The molar mass of zinc, if you just had to write the molar mass of zinc, would usually just be written in this version, 65.39 grams per mole. So, if you just had to write what the molar mass is, that is usually how you would display it. Here we're going to use it as a conversion factor. So we'll go with our 0.256 moles of zinc. Once again, we're just going to keep it simple and think about opposites. So I got moles up on top. I need to get rid of moles there on the bottom. So we're going to go opposite there, and we will go with our 6539 grams per mole of zinc. The moles of zinc will cancel. In this case, just like we did with conversions, we're multiplying whatever's on the top, right? And if we have something on the bottom, we're dividing, right, by whatever's there. So in this case, 0.256 times 6539, in this case, going to give us 16.7 grams of zinc. Once again, in both cases, this is the number we're looking at in terms of significant figures, as the molar mass really considered pretty much an exact number. So you would sort of ignore it. So we'd look at the first number, which has 3 significant figures in each of those. Any questions on either of those calculations there? All right, so why don't you try another one here then? You got, what we got there? We want to know, what is the mass in grams of one gold atom? And gold is something, 196.7. So if we look up gold on the periodic table, 196.7. All right, give it a calculation. Okay, so let's take a first look at this here. So we're looking for grams. We one gold atom by itself. So first off, do I need Avogadro's number here? I do. The keyword there is atom, right? So clearly I got an atom given to me, so I need to use Avogadro's number. So we want to think about a pathway to get us from basically atoms to grams. The one that sort of joins both of those things are moles, right? So that's kind of the bridge that joins both of them. So to go from atoms to moles, that's our Avogadro's number. Once we have it in moles, we go from moles to grams. That is our molar mass, right? That takes us kind of the rest of the way there. So we do need a few things here. We definitely need the molar mass on the back end of this calculation. And again, we could get that from the periodic table. And that basically means that there's 196.7 grams of gold in a mole of gold. Or you could use it again the opposite way. A mole of gold will give you 196.7 grams. We also need Avogadro's number. So in this case, 1 mole of gold here, there you go, is 6.022 times 10 to the 23 atoms. And again, you have this number always sort of available to you. Or you could do it the opposite way around, 6.022 times 10 to the 23 atoms over 1 mole of gold. So these are really our conversion factors that we could use to get us there. And we just want to kind of start with what was given, which is 1 gold atom. So the first thing that we want to do is to think about going from atoms to moles. So we want to get rid of atoms. So we are going to use the conversion factor here on the left-hand side to do that. Again, opposites will help us here. 1 mole of gold is 6.022 times 10 to the 23 atoms. If I stop the calculation right at this point, what units cancel? Atoms cancel, right? And the units I'm left with is moles at this point. And by again setting this up in dimensional analysis, we could clearly see moles are up on top, which means if I want to get rid of moles, I need to put moles now on the bottom, right? So in the opposite location. So again, that's why it's really important, as we talked about earlier, that you set up your calculations like this. It just makes the calculation easier. You don't have to think too much about it. We just got to think about opposites. So that means we will use the molar mass here on the left in this case. And that would get us our 196.7 grams of AU is a mole of AU. Again, the moles are opposite, so they will cancel each other out. We're now left with grams up on top, which is what we're looking for, which is good. Again, this comes from the periodic table, right? And that obviously is just given to you as Avogadro's number. At this point, all is left to do the math. So we're going to multiply whatever's on top. Remember, when we got multiple things going on, you're going to hit equals at the end of the top there. Then we're going to come back and divide by the bottom and hit equals, right? And in case that's 1 as well, you don't really need to divide by it, but you can if you want. So make sure you don't put too much in at once. This is basically going to be 196.7 divided by Avogadro's number, making sure to use your exponent button. And you are going to get, hopefully, my pen writes, here we go, 3.266 times 10 to the minus 22 grams in this particular case, if I got the right number there. Any questions on that there? All right. I think it's actually 197. I should have rounded that molar mass to. I'm getting old. I can't see the number on my periodic table, but it's 196.7. But it should round to about 197. It's pretty close. We'll go with it. Any questions on that there? All right, I went to 4 significant figures really in this case because that's pretty much an exact number. That's pretty much an exact number. If you have 1 of something, that's pretty much something counted, which is you could use as many significant figures as you want in this case. And looking back at the periodic table, small writing, but actually should have probably rounded it to 197. Would have been probably the better number there. All right, we'll go with the number I wrote there. Any questions on that calculation there? All right, let's try a couple more here just to make sure. Let's go with what is the number of molecules and 55.5 grams of C6H12O6. And we'll also do moles. Let's do that too. What's the number of molecules? Let's do moles first. What's the number of moles and molecules? There you go. And this guy, we'll do that. And let's just say we had 5.25 times 10 to the minus to the positive, actually, we'll do positive 14 molecules of CO2. How many moles and grams are there? All right, I'm going to try to look at the periodic table better this time and give you the right number that you see on the bottom there. All right, carbon should say 12.01. Hydrogen should say 1.008. Oxygen should say 16. And I think that's all you need. All right, give it a go. See what you come up with here on each of these. First one, we're looking for moles and molecules. Second one, we're looking for moles and grams. Okay, so since we're getting to kind of the end here, why don't you finish these 2 examples up at home and we'll talk about it at the beginning next time. Yeah, sound good? No, we won't have to rush through it or anything like that. Any questions on anything we talked about?